Hi everyone. This is the last topic we're going to cover in chapter 4. We're actually going to talk about cyclohexane and what are called chair conformations. But first, I wanted to go over a practice problem with Newman projections. So this will just kind of get our brains going here. So let's draw a molecule here. This molecule has 6 carbons in its parent chain. And then we have on the 3rd carbon a methyl group, as well as a hydrogen, of course. And on the 4th carbon, we have 2 hydrogens. And the other carbons have hydrogens as well, but I'm just drawing these specifically because we're going to look down this carbon-carbon bond, so carbons 3 and 4. Now remember, if we're just looking at these 2 carbons in the middle and we're going to draw a Newman projection, we also need to include these ethyl groups. So when you draw your Newman projection, you can abbreviate that as ET. And that way you don't have to draw the full ethyl group, which will make things a little bit easier. So I would like you to pause the video and try to draw a staggered conformation of this molecule. So it's Newman projection in its staggered form. And then when you unpause the video, we'll go over it together. Okay, so let's draw the staggered conformation for this molecule the way I drew it up above. So we're going to start with our front carbon. All right, so that again is this carbon here in red. So let's draw the ethyl group coming up. So it's in the plane, and I'm just again going to abbreviate that as ET. And then looking down below at our wedge and our dash, the wedge tells us that the methyl group is coming out towards us. So if we were to turn this molecule so that we're looking right down the carbon-carbon bond, that methyl group would be out to the right. Okay, and then the hydrogen is going back to the left. All right, so now let's draw a circle for our back carbon. And it looks like the hydrogens are kind of up above, so they're going right and left. One's coming out towards us, one's going back away from us. And then the ethyl group is opposite the other ethyl group. Okay. So let's draw the other 2 staggered conformations that we could have here. So instead of just turning one of the carbons 60 degrees to end up in an eclipsed conformation, let's draw the next staggered conformation. So we're going to turn the back carbon 120 degrees. So we're skipping the eclipsed and going straight to the next staggered conformation. All right, so if we're turning the back carbon, that means we're moving this ethyl group up. All right, so let's keep our front carbon the same. And now the back carbon has an ethyl group up and to the left, and then the other 2 bonds are hydrogens. Okay, so let's draw the next staggered conformation. So we'll do another 120-degree turn. So we're going to move the ethyl group again over. So our front carbon stays the same. And our back carbon now has an ethyl group up and to the right. And then the other two bonds are hydrogens. So looking at these three staggered conformations, which one is the most stable? And which one is the least stable? So if you want to pause the video and try to determine which one is the most stable and which one is the least stable, feel free, and then when you unpause, we'll go over it together. Okay, so let's look at our three staggered conformations. Which one is the most stable? The first one, right? Because those ethyl groups, those are the largest groups. And in the first conformation, they're as far apart as possible. Now, we do have some gauche interactions here between the methyl and ethyl group on the bottom, but we also have those in the other two conformations, so that doesn't really help us rule out which one is most stable. Remember, the most stable conformation will have the largest electron groups as far apart as possible. So in this case, the first structure is the most stable because those large ethyl groups are far away from each other. Okay, so now looking at our other two structures, which one would be the least stable? So let's consider the positions of our largest groups. If we look at our second structure, we do have gauche interactions between the ethyl groups. And if we look at our third structure, we have gauche interactions between our two ethyl groups and the ethyl and methyl group. So which one would be the least stable? The last structure, right? Because we want to limit the amount of gauche interactions that we have if we can. So that last structure will be the least stable because we have two gauche interactions. Okay, so you might see a question like this on an exam. For instance, you might be asked to draw Newman projections and determine which one is the most stable or least stable. So I just wanted to go over that practice problem before we move on to the next topic. All right, so now let's go on to our last topic for chapter 4, and that is chair conformations. And we're going to look at cyclohexane as our example. This is the most common monocyclic ring. So this is probably one of the most stable monocyclic rings. So let's draw the bond line structure for cyclohexane. So cyclohexane has 6 carbons and they're in a ring. So let's draw a hexagon. And if you were struggling to draw a hexagon, that's okay. It takes a lot of practice. I've just been doing this so long, and I still draw cyclohexane kind of odd sometimes. All right. Now, when we're looking at the bond line structure, we're looking from above. But what if we were to look at this sideways? So what if we looked down that bond and down the other opposite bond? What would that look like? Well, that would give us a Newman projection. So let's see what that would look like. So let's highlight this front carbon here in blue on each side. And we'll draw the back carbons in red. And then let's draw the middle carbons, we'll just highlight in black. Okay, so let's start with our blue carbons. So the first one on the left has, let's see, a hydrogen going up and one hydrogen kind of going down and to the left. And then we have a bond to carbon, and this is one of our middle carbons. So that one is right here. And now let's connect that to our other front carbon in blue. Okay. Oh, that's a really long bond. Let me fix that. It looks a little silly. There we go. That looks more symmetrical. Okay, so this carbon also has a hydrogen going up and then a hydrogen coming out to the right. All right, and now let's draw our back carbons. So I'll just draw a red circle for each of the back carbons. Or they kind of look like circles, I guess. So you'll notice that the two back carbons in our bond line structure are connected through another carbon. So let's just draw that connection in the back. So that back middle carbon is here in our bond line structure. All right, and now let's draw the hydrogens that are on each of these back carbons. So there will be a hydrogen kind of coming up and to the right and then down. And if we go to the left back carbon, there's a hydrogen coming up to the left and down. Okay, so that was really tough to draw, right? But this does show us what this molecule looks like from the side. So here we're looking at it from the side. Okay, so what if we kind of turn this structure at an angle? So what if we're kind of looking at maybe a 60-degree or 90-degree angle, something like that? That would give us something called a chair conformation. And I'll try to show you the three-dimensional structure of this as well in a separate video. So if you're having trouble visualizing this, don't worry. Hopefully the molecular modeling kit will help. All right, so if we look at this from an angle, we get something that kind of looks like, let's see if I can draw it well. Kind of looks like a bow tie almost. Actually, let me redraw this because I drew it kind of funny. It's been a while since I've drawn a chair conformation. But you start with two parallel lines. That's the better way to do it. And then you draw a little triangle kind of connecting those two lines. And that triangle will point down on the right, at least for this drawing. And then you'll draw another triangle kind of going up to the left. Okay, so then we have to draw all the hydrogens. So the hydrogens are going to either point up or down, or they'll point out at an angle. So let's start with this back carbon here in red. So that has, actually I'm going to draw its hydrogen going up just to make things a little easier, and you'll see why in a bit. And then we have one kind of coming out and down at an angle. And then for this front carbon, I'm just going to draw a hydrogen going down, and then one kind of coming up at an angle. All right, and then we have our middle carbons here. They're kind of flipped in this drawing, so I apologize if that's a little confusing. I'll show you another way to draw this as well. So this one, I'm going to alternate the hydrogens. So on the red carbon, the hydrogen was pointing up. The blue carbon, it was pointing down. So now I'm going to draw a hydrogen pointing up. And we can actually keep going around the structure. So the next one, we would draw a hydrogen going down. And then the next carbon, the hydrogen would go up. And on the next carbon, the hydrogen would go down. So the hydrogens alternate up and down around this ring. Now for the other hydrogens, let's go back to our middle carbon, our first middle carbon. You'll notice that the hydrogen we drew at an angle on the blue carbon to the right was kind of pointing up. So now we're going to draw our next hydrogen kind of pointing down at an angle. Next carbon, the hydrogen will point up at an angle. The one next to that, the hydrogen will point down at an angle. And finally, we'll have one pointing up at an angle on the last carbon. So this is our chair conformation, and this can be tough to draw, so you will want to practice this. But again, we're looking at the structure from above at an angle. Okay. So let me kind of walk you through how to draw chair conformations because I drew this fairly quickly and I want to walk you through how to do it in more detail. All right, so we'll want to draw first parallel lines, and they're going to be offset from each other. They'll also be at about a 60-degree angle. Okay, so we'll draw one line, and then we'll draw one kind of parallel to that, but they're sort of offset from each other. And then I'm actually going to draw little dotted lines here to make it easier to see. Okay, and then the second step, we're going to draw triangle connectors above and below. So I'll draw those in red. So we'll draw one triangle on the left, just kind of pointing down. And then we'll draw one pointing up. Great. So that looks a little a little funny, right? But this is a good way to try to draw it, and you can always erase and start over. So, this triangle is a little wonky, so maybe I'll just try to kind of redraw it there. So it almost looks like a folded up piece of paper, or another way to think of it is like a lounge chair. So one side is the headrest of your lounge chair, The other side is the footrest. But all lines should be parallel. So you can see mine aren't super perfectly parallel, but that's okay, as long as it's approximately parallel. And if you want more practice drawing chair conformations, I recommend going through Skill Builder 4.9 on page 162 of your textbook. Okay, so then where do substituents go? So you already saw me go through each of the hydrogens and drawing those, but let's go through that in more detail. Okay, so let me redraw the chair conformation that I just drew on the previous slide. And you can practice along with me. So I'm going to draw, let's see, I'm going to try to draw parallel lines here. I'm not the best drawer in the world, so, you know, it's okay if it's not perfect. You might have to make little adjustments. I don't like that. That's not a great one. Let's see, let me redraw my triangles. So see, even I'm messing this up. It can take some practice here. We'll do that, I guess, and then we'll draw one kind of going up. Okay, that's a little bit better. And it does kind of look like a bow tie that's shifted a little. Okay, so now let's draw some substituents. So where would those go? Well, number one, we're going to add bonds straight up for carbons that are pointing up. So actually, if we go back to my original drawing, you'll notice that all of the carbons that were pointing upwards had hydrogens pointing upwards. So on the red carbons in particular, those were kind of pointing up, so the hydrogens were pointing up. All right, so let's draw those. And I'm actually going to label these as A. Now you'll also notice that each of these carbons are one bond or two bonds apart from each other, so we're skipping every other carbon. Okay, so step one, draw bonds straight up for carbons pointing up. And then similarly, we're going to draw bonds down for carbons pointing down. And I'm also going to label those A. Okay. So A actually stands for axial. So if you have a substituent pointing straight up or straight down, we refer to that as an axial substituent. Now next, we're going to add substituents on at an angle on each carbon. But what we're going to do is make sure that they're parallel to adjacent carbon-carbon bonds. So stick with me here. I'm just going to write that down. So draw the other substituents so they are parallel to adjacent carbon-carbon bonds. Okay, so for instance, let's start on the right-hand side, the bottom carbon. We're going to draw the bond kind of pointing up and at an angle, and that's going to be parallel to this line over here. So that's kind of our adjacent carbon-carbon bond. And I'm going to label this as E. And E stands for equatorial. So if you have a substituent at an angle like that, or really at any angle, so anything that's not pointing straight up or straight down, we call that an equatorial substituent. Okay, so now on the back carbon directly behind that, we're going to draw a bond going kind of down at an angle so that it's parallel to the bond back here. And we'll also label that as equatorial. All right, and then we're going to do the same thing on the next carbon. So if we kind of look 2 bonds over, we want this to be parallel to this bond, for instance, or even this bond over here on the right. And then that will also be labeled equatorial. Sometimes I draw that back bond a little bit differently, so you know, I'll know what you mean if you don't draw it exactly the same way here, but try to be consistent, I guess. Okay, and then the next one, we're going to draw this bond down parallel to 2 bonds over. So that's also an E, equatorial. And then finally, oh, I guess we have 2 more here. So the next carbon, we want that bond to kind of point up and over, similar to 2 bonds away. So that will be equatorial. And then finally, we have our last bond. So this one will kind of point down, similar to the left or right bonds in red. And that is also equatorial. Okay, so this is how we draw the chair conformation for cyclohexane. And again, this is really important because this is going to tell us a lot of information about the substituents on a cyclohexane ring. Are they pointing up? Are they pointing down? So let's say we have multiple substituents. Are they all pointing up? Are they all pointing down? And that can have a huge effect on reactions and how reactions occur. So this is really important going forward. Right now it might seem a little arbitrary. Why are we drawing this? Why do we care? But it will come up again in the future. Okay, so what happens if we flip the chair? So let's talk about that. Chair flip. All right, so I'm just going to redraw the chair conformation, but I'm only going to draw 2 substituents. So let's see, we'll draw our parallel lines and our triangles. Again, it doesn't have to be perfect the first time you do it. I'm still not good at it, so but let's just draw our equatorial and axial substituents on this front carbon here. Okay, now the ring can flip. So if we flip the ring, what ends up happening is this front carbon essentially moves to the back, and then this back carbon on the opposite corner moves to the front. Now this might be hard to visualize, so what I'll do is in my other video after this, I'll show you a 3-dimensional model and flip it for you so you can kind of see what's going on. So bear with me for now. Now a chair flip can go back and forth, and this is something that cyclohexane does naturally. So it can flip its configuration a bit. So what we end up with is basically a mirror image here. So I'm going to draw a mirror image. Oof, if I can. This is tough. Okay, so we've got our parallel lines going the other way, and then I'm going to draw an up triangle on the right and a down triangle on the left. So we flipped everything, and now our front carbon with the substituents is in the back. And then our other carbon that we highlighted in green is in the front. Now what also happens is our equatorial substituent becomes axial. And then our axial substituent becomes equatorial. So let's actually relabel those so that we don't get confused. So let's label these, let's just label them C and D. That's a little bit easier. And then we won't get the axial and equatorial terms mixed up. Okay, so our substituent C was originally axial and pointing down, but now it's going to be equatorial pointing down. And then our equatorial substituent, labeled D, is now going to be axial. It's still pointing up, but it went from equatorial to axial. So after a chair flip, axial becomes equatorial. And then equatorial bonds become axial. All right, and this is going to have an effect on future discussions. So it is important to understand how this works, although it might seem a little bit weird right now. Why are we talking about cyclohexane so much? But it does come up again. Now let's talk a little bit about the stability of these different positions. Is axial more stable than equatorial or vice versa? But if you do want to practice this a little bit more, I recommend Skill Builder 4.11 on page 164. Okay, so let's talk about the stability of these positions. All right, so let's draw a cyclohexane molecule with some substituents. So let's just draw some methyl groups. And let's say that one is kind of coming out towards us at the top. And then let's put one on the second carbon, and it's going back away from us. So let's actually take a minute and name this molecule for some practice. So remember, if you have a monocyclic ring, you want to count all of the carbons in your ring. So we already know that this is cyclohexane, right? So we can start with that. But we want to number this so that the substituents are on the lowest numbers possible, or have the lowest numbers possible. Okay, so let's just start at the top, 1, and then we want to go clockwise, right? So that the second methyl is on carbon 2. Because if we went the other way, that second methyl group would be on carbon 6, and we don't want that because that violates our rules. Oops. I almost erased a bond. All right, so we're going to go clockwise for this one so that the substituents have the lowest numbers possible. All right, so we would call this 1,2-dimethyl cyclohexane. But actually, there's one more thing we have to indicate. So you'll notice that one methyl group again is coming out towards us, one's going back away from us. So we want to call that a trans molecule. So trans means opposite sides. And then if those two methyl groups had both been pointing towards us, or if they had both been pointing away from us, we would call that cis. So that means same side. Okay, so since we have two methyl groups that are pointing in opposite directions, we call that trans 1,2-dimethyl cyclohexane. Okay, so let's draw this as a chair conformation. So I'm going to draw my parallel lines, my triangles pointing down and pointing up. And let's just label each of the carbons around this ring. So I'm just going to start in the upper back corner. So 1, 2, 3, 4, 5, and 6. Okay, so if we start with carbon 1, we have a methyl group that's pointing towards us. So I'm going to say that that is up above the plane of the cyclohexane ring. So again, the wedge is indicating that the methyl group's up above or coming out towards us. So we want to draw the methyl group as axial on that back carbon. And then of course there's a hydrogen behind that, so we'll draw that kind of down at an angle. And then the other methyl group, the wedge methyl group, that's going down away from us. So we're going to draw that on carbon 2, also axial. So it's down and away. And then, oops, what just happened? I clicked on something. And then the hydrogen is coming up at an angle. Okay, so let's figure out if this is stable. So let's draw the hydrogens on the other carbons that are nearby. So I'm going to draw a hydrogen coming up on carbon 5, and then I'll also draw one coming down on carbon 4. And then let's draw one kind of coming down behind here on carbon 6. And then we'll draw one kind of coming up on carbon 3. So it looks a little messy, but I want to show that the hydrogens are really coming up, and they're kind of mirroring the methyl group there. So this is actually not very stable because this methyl group on the top is really close to the hydrogens that are also pointing up on every other carbon. And the methyl group on the bottom is also really close to the hydrogens down below. Now it doesn't really look like it given our drawing here. It looks like there's a lot of space there, but I'll show you what it looks like on our 3D molecule. And you'll see that the CH3 group is actually really big, and it's going to have what are called 1,3 diaxial interactions with those hydrogens. And those are destabilizing. You could even imagine that those hydrogens are other methyl groups. So if you have a bunch of really large substituents hanging out above or below the plane of this molecule, they're all going to run into each other and it's really unstable. So let's actually do a ring flip or a chair flip, and let's show what this would look like if everything was equatorial. So remember, when we do a chair flip, axial bonds become equatorial, equatorial bonds become axial. Okay, so we're going to do a little chair flip here down below. So I'm drawing the opposite chair from before. So let me highlight up above our front carbon in blue and our back carbon in red. So the blue carbon is going to shift back one spot, and then the red carbon is also going to shift over one spot when we do this chair flip. So on the blue carbon, CH3 was down and axial, and now we did a chair flip, so it's still going to be down, but it's going to be equatorial. And then the hydrogen will still be up, but it will now be axial. And then on the red carbon, the methyl group was up and axial, and it will still be up, but it's going to be equatorial. And then the hydrogen was pointing down and it was equatorial, but now it's going to be pointing down as an axial bond. Okay, so now that the methyl groups are equatorial, let's draw some of the other hydrogens around the ring. So we would have some pointing up and down, up. Oh, wait, that one's not up. I did it wrong. Even I get confused on these sometimes. This would be up and equatorial. This one would be down and axial. And then on the back one, it's pointing up, down. So you can see that these methyl groups, or hopefully you can see that these methyl groups aren't really running into anything anymore when they're equatorial. They're just hanging out kind of in their own space. And again, I'll try to show you in my next video what that looks like on a three-dimensional structure. So what this tells us is that it's more stable if your substituents are on equatorial positions. So equatorial is more stable than axial. And let me actually highlight up above 1,3 diaxial interactions are destabilizing, and kind of point up above. I don't want you to mix that up with what I drew down below. That's separate. So again, the main message here is if you can place your substituents in an equatorial position, that will be much more stable than if they're in an axial position. And that's due to those 1,3 diaxial interactions. So if you want more practice with this, I recommend trying Skill Builder 4.10 on page 163. They probably also have better figures than what I just drew, so that might help you kind of clarify some things. But that's really it for chapter 4. In the next chapter, we're going to talk about something called chirality, but don't worry about that just yet. Just focus on studying for the exam. And I will also post another video showing you the three-dimensional structures of these cyclohexane molecules. So I will see you then.